I was actually looking at my hand this morning.
Just staring at it.
Yeah, just staring at it while I was drinking my coffee. And I was noticing the way the skin stretches over the knuckles, the way the thumb rotates. Just the sheer mechanical complexity of it all. It really is an engineering marvel.
It absolutely is.
And it got me thinking about what is arguably the absolute holy grail of medicine.
Which is?
Well, it's not a better prosthetic. It's not a robotic arm that connects to your brain, as cool as that is.
Right.
I'm talking about the pure sci-fi dream. You lose a limb, and instead of getting fitted for plastic and servos, the doctor hooks you up to a machine, and your body just grows it back.
Bone, muscle, nerve, skin.
Yeah.
Everything.
Exactly. A perfect biological copy of the original.
A lizard tail trick.
Yes, the lizard tail trick, but for humans. And for the longest time, we've been told by everyone that this is biologically impossible.
Because humans scar, we heal, but we do not regenerate.
Right. But then I read this paper you sent over for today's deep dive. And I have to admit, it felt like I was reading a technical manual from the year 2050.
It really does feel that way, doesn't it?
It's wild.
It's an incredibly dense read, but for those of you listening, the implications here are massive. The paper is titled, and get ready for this mouthful, okay?
Yeah, go for it.
It is Directed Autologous Limb Regeneration via the MicroneedleOptogenetic Hydrogel interface and the Stagnant Starvation Building Protocol.
That is quite the title.
It's a lot.
It is a lot, but we are going to unpack every single word of it today because what they are proposing is terrifyingly cool.
It really is.
We aren't just talking about biology here. This isn't, let's put some cells in a petri dish and hope for the best.
No, not at all.
This is about turning the human body into a programmable machine using a mix of wetware like hydrogels and hardware like electronics.
And that is the core mission here. The authors are basically arguing that regeneration shouldn't be treated as this magical biological event that we just cross our fingers and hope for. They want to treat it as a strict engineering discipline, a fully programmable process with very specific inputs, outputs, and most importantly, safety switches.
Okay, but before we get to their solution, which, by the way, involves starving cells and shocking them with electricity, we have to talk about the problem.
We do.
Because why haven't we done this yet? We can clone sheep, we can transplant hearts, we edit genes now.
We do all of that.
So why can't we regrow a single finger?
It basically boils down to two major roadblocks, and they are actually evolutionary safeguards.
Safeguards.
Yeah. When a human suffers a massive injury, like an amputation, the body panics. Its number one priority is survival, not restoration.
It just wants to stop the bleeding immediately.
Precisely. So it prioritizes patching the hole over fixing the wall. And that's roadblock number one, fibrosis.
Scar tissue.
Exactly. The body throws down this messy web of collagen just to seal the breach. It's highly functional in the short term because it keeps your insides in.
Always a plus.
Always a plus. But it blocks any chance of real regeneration. It's a chaotic patch job.
Okay, so the body panics and scars over. What is roadblock number two?
Oncogenesis.
Cancer.
Cancer. See, to grow a whole limb, you need stem cells to divide rapidly, millions and millions of times to create that much tissue.
Right.
But biologically speaking, rapid, unchecked cell division looks a whole lot like a tumor.
So if you just injected a bunch of growth serum into an arm, you're just as likely to get a massive teratoma as you are a functional hand.
Historically, yes, those were your options, a useless scar or a deadly tumor. This paper proposes a highly complex system to navigate exactly between those two disasters.
So let's get into what they call the soil. If we're going to grow an arm, we need something to plant the seeds in.
Yeah.
Paper talks about this MOH interface.
Right, the MicroneedleOptogenetic Hydrogel interface. So usually in tissue engineering, you use 3D printing.
Right, you print a scaffold in the shape of a bone, put cells on it, and wait.
Exactly. But this paper argues that 3D printing is dead.
Dead. That seems a little harsh considering how hyped 3D printing still is.
Well, think about it from a biological perspective. A 3D print is static. It's a statue.
Okay.
Once you print a plastic scaffold, it stays that exact shape. But a growing limb is incredibly dynamic. It needs to be soft at first to let the nerves move in, but then it needs to get hard to support bone.
Oh, I see. A static 3D print can't do that.
Exactly. So they are using 4D bioprinting.
And I assume the fourth dimension here is time.
You got it. They're using fourth-generation biomaterials, specifically a substance called GELMA.
GELMA. That's gelatin methacryl oil, right?
That's the one.
which honestly just sounds like high-tech Jell-O.
It's remarkably close to that. It's a hydrogel.
Yeah.
But the 4D part means this jelly changes its physical properties based on external stimuli.
Like what?
Things like pH changes, temperature shifts, or even light. It's not building a statue, it's building a transformer. It actively adapts as the tissue grows.
But here's the thing that really caught my eye in this section. A jelly is just, well, it's just goop. It acts as a home for the cells, sure, but it can't send signals. And if we're trying to actually program this limb, don't we need wires? The paper mentions MZenes.
Yes, MZenes. That stands for two-dimensional transition metal carbides.
Okay.
Imagine nanosheets made of alternating layers of titanium and carbon.
Wait, titanium layers inside the jelly?
Tiny microscopic layers, yes. And this is crucial because biology runs on electricity.
Right. Nerves firing, muscles contracting.
It's all voltage. Normal plastic scaffolds or plain hydrogels are insulators. They block that electricity. By adding these MZene nanosheets, the scaffold becomes conductive.
It basically turns the scaffold into a circuit board.
Exactly. It creates an active electronic interface. It allows the scaffold to feel mechanical forces, but more importantly, it allows the computer to talk to the cells.
Wow.
It is the literal bridge between the digital control system and the biological tissue.
So we've got a 4D smart jelly wired up with titanium nanosheets. That is the soil. Now let's talk about the actual process. They call it the SSB protocol. Stagnant, starvation, build.
There are 3 phases of creation.
I have to say, stagnant and starvation are terrible marketing names for a healing process.
They really are.
I mean, stagnant usually means a pond full of mosquitoes. Why start with that?
It does sound completely counterintuitive. But phase I, the stagnant phase, isn't about doing nothing. It's about anabolic sensitization.
Okay, break that down for us.
Before you can build the house, you have to run the electrical lines. This entire first phase is focused purely on connecting the patient's existing nervous system to this new scaffold.
How do they coax the nerves to grow into a block of jelly, though? Because nerves are notoriously picky. If you cut a nerve, it usually just curls up and dies.
They use that conductive interface we just talked about. They use a microneedle array to send a continuous electrical pulse through the gel, specifically a 2 Hz signal.
Just a steady beep, beep, beep.
Essentially, yes. That 2 Hz pulse acts as a beacon. It's a guidance cue. It literally tells the nerve axons in the amputation stump, hey, come over here.
Does that actually work better than nature?
Significantly better. Peripheral nerves usually grow at a painfully slow rate of about 1 millimeter per day.
Right.
But the data in the paper shows that this 2 Hz signal boosts motor conduction velocity and dramatically increases the number of motor units that actually connect. It's like putting a superhighway sign up for the nerves.
So it drastically speeds up the wiring process.
And it does one other crucial thing while it's doing that. It establishes a baseline.
A baseline for what?
While it's pulsing, the system is actively reading the bioimpedance of the tissue. It's learning the specific electrical resistance of that particular patient's cells.
Like an electrical fingerprint.
That is a great way to put it. And that data becomes the safety profile for everything that comes next. Because phase two is where things get incredibly risky.
Phase 2 starvation. This is the part of the paper that really made me pause. Why on earth would you intentionally starve a growing limb?
It sounds backwards.
It really does. If I want to get big muscles, I eat protein. I don't stop eating.
You're thinking about building bulk. But remember those 2 enemies we talked about at the start? Fibrosis and cancer.
Right, scar tissue and tumors.
Phase 2 is specifically designed to defeat them.
By starving them out.
Yes. They use microfluidic channels, tiny tubes embedded inside the jelly to physically restrict nutrients. They cut off the food supply. This induces what they call a catabolic crisis.
That sounds incredibly dangerous.
It is controlled danger. When you starve a cell, it triggers a biological process called autophagy.
Self-eating.
Right. The cell realizes it has no outside resources, so it starts cleaning house. It recycles its own waste. But more importantly, this state of deep crisis shuts down the specific pathways that create scar tissue.
I saw the term YAPL33 signaling axis in the paper. I assume that's the path.
That is the villain here, yes.
Yeah.
The YAPL33 axis is the signaling pathway that yells at the body, emergency, make a scar right now.
It triggers that panic response.
Exactly. Starvation effectively cuts the power to that alarm. It forces the body to stop making disorganized, messy scar tissue, which is type I collagen, and start making elastic, highly structured tissue, which is type 3 collagen.
So by radically stressing the system, You force it to be more efficient. It's like lean manufacturing for biology.
That is a perfect analogy. You are stripping away all the noise.
But wait, if you're starving the cells, aren't you worried they'll just die? Or worse, mutate?
You said earlier that stress and rapid division causes cancer.
It does.
If I'm a cell and I'm starving, I might mutate just to survive the crisis.
That is the massive risk here. Starvation places huge evolutionary pressure on these cells. And sometimes desperate cells turn cancerous to survive.
So how on earth do they stop that from happening?
They have built a biological firewall, and honestly, this is probably the most impressive piece of engineering in the entire paper.
Let's hear it.
It's essentially a mix of a shield and a sword.
Okay, let's break that down. Start with the shield. The shield relies on optogenetics. They shine a steady blue light on the engineered cells. Now, these specific cells have been genetically modified with proteins like GTACR1.
Okay.
When that continuous blue light hits them, it forces them into a deep state of quiescence.
Quiescence, so biological sleep mode.
Basically, technically, it causes hyperpolarization of the cell membrane. It makes the cell very hard to activate.
Got it.
It essentially tells the cells, don't try to divide, don't try to grow, just sleep, save your energy. This protects the good stem cells from burning out or mutating during the starvation phase.
Okay, so the blue light keeps the good guys safe in a bunker. What about the bad guys? The cancer cells?
That is where the sword comes in. The kill switch. Remember that bioimpedance baseline we established back in phase I?
The electrical fingerprint.
Exactly. The computer system is constantly monitoring that exact resistance. Healthy, organized cells have a very specific, steady resistance, but cancer cells,
They're different.
they are highly chaotic, they have leaky membranes, they are completely disorganized. When cells start acting like cancer, the electrical resistance in that area plummets.
So the system can literally see a tumor forming just by looking at the flow of electricity.
Yes. The paper sets a very specific, rigid threshold, 450 ohms. If the bioimpedance drops below 450 ohms at any point, the system knows something is wrong. It knows cells are dividing chaotically when they shouldn't be.
And what happens then?
It executes the kill switch. The microneedle array instantly fires an IRE pulse irreversible electroporation. It hits that specific localized area with 700 volts per centimeter.
700 volts. That sounds like it would just fry everything.
Well, that's the beauty of the shield we talked about. The good cells are actively hyperpolarized by the blue light. They're essentially electrically insulated against the shock.
Oh, wow.
But the active cancerous cells, they are wide open. The high voltage instantly blows microscopic holes in their cell membranes, killing them completely.
It's an automated sniper rifle for cancer.
That is a perfect description of it. It is a completely closed-loop system. The computer detects the microscopic risk and eliminates it before a human doctor would ever even notice a lump.
That is wild. So phase 2 is basically a biological boot camp where we starve the tissue to stop the scarring, while a computer watches with an electrical sniper rifle to make sure absolutely nothing turns into cancer.
Vivid, but highly accurate.
So, assuming we survive the starvation phase, which it sounds like we do, we move to phase 3. Building the regenerative rebound.
Now the crisis is officially over. The microfluidic channels open back up and nutrients flood back into the gel. The cells wake up.
Right.
And because they've been through that intense cleanup phase, they are completely primed to build pure functional tissue.
But a human limb isn't just a blob of meat. It needs incredibly strong bone and very fast muscle. How do they ensure the bone is actually hard? You can't just feed a cell and hope it randomly becomes a femur.
You're absolutely right. Bone requires physical stress to harden. It's a biological rule called Wolff's Law. It's the exact reason why astronauts lose bone density in space. No gravity, no stress, weak bones.
Right.
But this patient doesn't have a functional limb yet to walk on.
So they have to fake the gravity somehow.
They fake it with physics. The system actually starts vibrating the entire scaffold. Specifically, it vibrates between 12.5 and 50 hertz.
They literally shake the arm into existence.
At 50 hertz, combined with a 0.5 G acceleration, the gene expression for bone mineralization, specifically the alkaline phosphatase gene, increases by 4.5 times.
Just from the vibration alone.
Yes. The cells feel the mechanical vibration, and they interpret it as the physical stress of walking or lifting a heavy weight. So they immediately start laying down hard mineral deposits to reinforce the structure.
Okay, that handles the bone. What about the muscle tissue? Because you can't just vibrate a bicep into existence, can you?
No, muscles are different. For the muscle, they go back to the lights. In phase 2, they use that steady blue light to put cells to sleep. In phase 3, they switch to high-frequency optogenetic pulses.
Like a strobe light.
Exactly like a strobe. High-speed, rhythmic flickering. These pulses stimulate the cells electrically, perfectly mimicking the neural load of intense, sustained exercise.
So the arm is basically running a marathon while the patient is just lying there in bed.
It forces the cells to fuse together into functional, highly structured, fast-twitch muscle fibers. It is optical pacing. You are programming the tissue to become strong purely through the medium of light.
This entire process, I mean, the deeper we get into it, the less it feels like traditional medicine and the more it feels like computing, or even physics.
That observation hits exactly on the core philosophy of this entire paper. And this is where the authors get really philosophical. They call the whole concept thermodynamic gating.
Yeah, I saw that section towards the end. It got a little heavy on the physics. They mentioned Maxwell's demon. I vaguely remember that from college physics, but help me out here.
It's a very famous thought experiment from the 1800s. Imagine a sealed box full of gas molecules just bouncing around in total chaos. That chaos is entropy.
Okay, chaos equals entropy. Got it.
Now imagine a wall right in the middle of that box with a tiny door. And a tiny demon controls that door. He watches the molecules. If a fast, hot molecule comes by, he opens the door and lets it through to one side. If a slow, cold one comes, he shuts it.
So he's actively sorting them.
Right. He is creating order out of pure chaos just by controlling the flow of information. He fundamentally lowers the entropy of the system. In this regeneration protocol, the computer is the demon.
The computer is the demon.
Think about it. Biology is naturally chaotic. Left entirely to its own devices after a traumatic amputation, it makes mistakes, it makes scars, it makes tumors. That is a state of high entropy.
So this whole stagnant starvation building protocol is just the computer demon sorting the biological molecules.
Exactly.
Wow.
Phase I synchronizes the system. It gets everyone on the exact same page. Phase 2 heavily restricts the entropy. By starving the system and using the kill switch, the computer physically prevents the chaos of cancer. It acts exactly like a bouncer at a club, refusing to let the chaotic elements in.
Right.
And then phase 3 takes all that stored potential energy and channels it into what they call genome engine work, building the highly ordered structure of the bone and muscle.
So it's treating the human body exactly like a thermodynamics problem. If you control the energy and the information flow, you absolutely control the final result.
Precisely. It completely transitions limb regeneration from a random biological process, let's just hope this heals, to a highly predictable, programmable engineering discipline.
It is incredible to think about. We started this conversation with a tub of gelatin and some microscopic titanium sheets. And by strictly controlling the environment, starving it, shocking it, vibrating it, we end up with a fully functional human arm.
And not just any functional arm, but an autologous one made entirely of your own cells. No immune rejection, no lifetime of immunosuppressant drugs.
So let's just recap this journey for everyone listening, because there were a lot of moving parts today. We start with the soil.
The MOH interface. A 4D printed smart gel heavily wired with conductive enzymes to carry electrical signals.
Then we move into phase 1. The stagnant phase,
where we use a 2 Hz electrical lure to coax the severed nerves in, and we learn the patient's unique electrical signature.
Then phase 2, the starvation phase, the scariest part.
We completely cut the food supply, triggering autophagy to stop all scarring. Meanwhile, that biological firewall keeps the good stem cells asleep with blue light and zaps any emergent cancer cells with high-voltage electricity if the bioimpedance drops below 450 ohms.
And finally, phase 3, the building phase.
We bring the food back, vibrate the bone to physically harden it, and use optical strobe lights to exercise the muscles into existence.
It is a lot to take in, but it paints a very clear picture of a future where losing a limb is just a temporary technical difficulty, not a permanent disability.
It fundamentally changes the definition of patient care. Yeah. We aren't just nurturing the body anymore, hoping it does the right thing. We are actively debugging it. We are compiling human tissue exactly like we compile computer code.
And that leads me to the thought I want to leave everyone with today. The paper actively talks about the human genome as an engine that is driven by information loops. If we can hook a computer directly up to our cells, read their electrical output in real time, and program their physical growth with light and starvation.
Yeah.
If we can engineer a biological arm with the exact same precision that we engineer a robot arm, are we approaching a point where the distinction between a biological limb and a manufactured machine just stops making sense entirely?
That is the big question. When biology becomes that programmable, the line blurs completely, and we might just be standing right on the starting line of that new era.
Definitely something for you to think about next time you look down at your own hand. Thanks for diving in with us today.
A pleasure, as always.